you'll be able to differentiate between the three main types of isomerism. In addition, you'll be able to tell when a double bond contributes to isomerism, specifically cis-trans isomerism. And finally, you'll know the differences between enantiomers and diastereomers. Take 1 minute to read this question stem now. Here, it's important to recognize that there's a lot of background information that's not actually necessary to answer this question stem. All we really need to do here is to determine the type of isomers we're dealing with. From there, we'll be able to extract where the enzyme works. So let's get started. Before we go on our hunt for the right type of isomer, let's make sure we have a solid understanding of the three classes of isomers that exist. That'll make our upcoming work much easier. All the isomers that you know, or that you've ever heard of, all fall into three categories. I like to remember that by thinking that you have three C isomers: conformational, configurational, and constitutional. The isomers that we call stereoisomers include conformational and configurational isomers. Another trick here, you can remember those 3D isomers by knowing that those are your confisomers, so conformational and configurational. Let's look at conformational isomers first. We have two molecules of glyceraldehyde shown in what's called Newman projections. These are especially useful when looking at conformational isomers, since you can see how the substituents of two bonded carbons stack up spatially. How are these molecules of glyceraldehyde different from one another? Well, we see that basically, if you just rotate the sigma bond and keep the front substituents at the same place, it's just the back substituents that are rotating. So what can we say about whether bond breaking is required for these isomers? We said it's just a simple rotation of a sigma bond, so no bond breaking is required, which also means that it's the same molecule with the same connectivity. And that's why I like to think of conformational isomers as yoga isomers. When you do yoga, or if you were to do yoga, you'd just be placing yourself in different positions, but your limbs would always be connected in the same way since you can't really disconnect them in the first place. Next up, we have our configurational isomers. What's the difference in these two sugar molecules? Our middle carbon is the only thing that looks different here. The molecule on the left has the hydroxyl group or the OH group on the right, and the molecule on the right has it on the left. So what's required here to go from one molecule to another? Well, we need that bond breaking here, because even if it seems like we can just do a quick horizontal rotation, remember, this is a Fischer projection, so it's a simplified view of the 3D molecular geometry, which is tetrahedral. In other words, there's no way we could rotate any bond so as to make these two molecules have the same 3D configuration. However, in terms of each atom substituents, that's the same for both isomers here. And finally, we have our constitutional isomers. It's apparent here that the carbonyl groups don't even show up on the same carbon, so we're not even dealing with the same molecule. On the left, we have glyceraldehyde, but on the right, we have dihydroxyacetone. Cool little fact here, these are the only 2,3 carbon sugars that exist. So we would definitely need bond breaking to go from one molecule to the other, and the connectivity is definitely different. So now take a look at this table. What seems to happen to our isomers as we go from left to right? The isomers are becoming less and less similar. Conformational isomers are basically the same molecule that's twisted in different ways. Configurational isomers have different 3D arrangements, and constitutional or structural isomers are just united by the fact that the molecules share the same molecular formula. This is actually a great summary table, so feel free to refer back to it as much as you need. So we can start looking for ibuprofen's isomer type. The question prompt's already telling us that we're not dealing with either conformational or constitutional isomers. Why aren't we dealing with conformational isomers? The question stem tells us that we need an enzyme to convert ibuprofen from one isomer to another, which means that bond breaking is required, and we know that we don't need bond breaking with conformational isomers. What about constitutional? Why can't ibuprofen isomers be constitutional? Both ibuprofen isomers are referred to as ibuprofen, which means that they have the same connectivity. Constitutional isomers do not have the same 2D connectivity, and therefore do not and cannot have the same name, so that option can be eliminated. Since we've narrowed our options down to configurational isomer, we need to see whether ibuprofen is an optical or cis-trans isomer. In order to have cis-trans isomerism, we need double bonds. Let's look at our ibuprofen molecule to see what double bonds we're dealing with. First, we notice clearly the benzene ring double bonds. You might have a gut feeling that this can contribute to cis-trans isomerism, but why? What configuration must this ring be in? It absolutely must be in cis configuration. So let's take a look at these two carbons right here. We see how their carbons are in cis form. And we also see that having a trans form would break our ring. So really that's why you don't hear about the cis configuration of the benzene ring. Because all carbons must form the ring, so be bound together, and there's no way that that can happen but with a cis configuration. Next up, the carbonyl group. That double bond is also not a source of cis-trans isomerism. Why not? We don't have any substituents on the oxygen atom, and it's the substituents that help us determine the cis or trans configuration. Bottom line, no substituents, no cis-trans. So we've considered all of our double bonds, none are a source of cis-trans isomerism, so we must be dealing with optical isomers. Final step to narrow down here. What accounts for both enantiomers and diastereomers? It's the chiral carbons. You'll also hear those referred to as stereocenters. Basically, they are carbons that are bound to 4 different substituents. So let's look at our ibuprofen molecule again and count our chiral carbons. There's only one here. So let me ask you this. What are diastereomers? You have diastereomers when you have 2 configurational isomers that have different configurations at 1 or more, but not all of the stereocenters and are not mirror images of each other. It's not possible to satisfy this diastereomer criterion here because we only have one stereocenter. And there we have it. By eliminating, we were able to narrow it down and find that our ibuprofen isomers are in fact enantiomers. And we're also able to tell that the AMACR enzyme from our question stem acts on that particular chiral center. Enantiomers are hugely important in pharmacology, and you'll learn about a bunch of drugs whose enantiomers have different properties. It's going to be a whole lot of fun to get to study those, but for now, let's wrap up this lesson and consider the 2 biggest differences between enantiomers. The first thing that should and probably does pop in your mind when you see something like enantiomers should be the idea of plane polarized light. Specifically, 2 enantiomers will rotate light to the same degree, but in opposite directions, either clockwise or counterclockwise. In the question stem, we were told about dexibuprofen, and because of its prefix, you can tell that it's going to rotate plane polarized light clockwise, which is often represented by a plus sign. In fact, you could have guessed right from the get-go that we were dealing with enantiomers just because of that name. And if you did, props to you. That's exactly the type of observational skills that you'll be rewarded for on your MCAT. Then of course, we also have levibuprofen. Levi, which kind of sounds like left, is the typical prefix used for the enantiomers that rotate plane polarized light left, so counterclockwise. And that's illustrated with the negative sign. You can remember that by thinking that being gauche, which is French for left, is typically not a great thing, hence the negative sign. The other difference, which is something that's hinted at in the question stem, is that enantiomers might have different behaviors and do different things in chiral environments. Now, since I've given you a hint, you tell me, what's the chiral environment that was presented to us in the question stem? It's the human body. So concretely, what's a chiral environment? It's something that in some way allows us to tell the difference between 2 enantiomers. So we're told that dexibuprofen is biologically active, pointing out the fact that levibuprofen isn't. So in other words, by putting these different enantiomers in the body, you can tell which one is which based on whether you see enzyme inhibition or not. How interesting is it that a simple change in configuration at the chiral center in this whole molecule will literally be the make or break for biological activity? As promised, we've contrasted conformational, constitutional, and configurational isomers. In addition, we've determined what's required in order for a double bond to contribute to cis-trans isomerism. And finally, we've investigated the differences between enantiomers